How's everybody doing? Sorry, I'm a little late. I had left my laptop charger at home and I'm here on campus, so I had to go back to the lab. Okay, so let's check out our lab assignment for today. If you can go ahead and download that. 1 second. I'm gonna log in real quick. 1 second. Okay, so we are going to work on Unit 7 lab, which is going to be on search and sort. Go ahead and download this because I don't have Okay, so let's talk about the binary search to start. Here what we have is we are going to have the search for the array. As we talked about binary search on Tuesday, we talked about how we would take that array and we would divide it in half until it's going to be small enough where we can actually seek the key value. So what you have is you're going to have the array and you are going to divide it in half. So you have to find the middle interval. And then you are going to look at the lower half and compare to the upper half. So in this case, if we're looking at this array, we are going to have 16 as the interval. And because 23 is greater than 16, we would be able to, we're going to take this and we're going to divide this into the second half, and the upper half is going to be this. So that's going to be our cutoff point for the half. Okay, so then we would have two subarray. Then we are going to go through and we're going to cut it up again into half and a second half. So now what you have for the lower half, 56, is going to be the middle element. So in this one, we want to focus on where our half interval is going to be. And so that way we will be able to divide it. So then in the next iteration, we would then find the middle interval again. That will be 23. And so once you get here, you have two numbers. And so that means that you can stop there. Okay. So now when you take a look at that, this is going to be our calculation, our formula for how to be able to calculate TFN. So in example 1, when you're looking at this program, it's pretty simple in that you're only going to have a function and a main. So here, what we're going to do is we are going to write a function, and our function is going to accept integer. So it's typed as integer. And keep in mind that we are implemented two STL. One is going to be the algorithm, and the second is going to be the array. The reason why is we want to be able to utilize some of the the components from these libraries, such as size of, that's where we want to implement the array here. So it's going to look at the number of the elements in your array. And of course, when you implement an equation, you have to implement the library algorithm or the STL algorithm. Okay, so you simply define a function which is called binary search. In this function, its parameter, its arguments is going to be the array, which is ARR here. And we are going to have three variables. That's going to be L, R, and X. Okay. Then inside the function, we're going to have a while loop. And what this will do is it's going to allow us to really identify where the middle mark is going to be, which element is going to be the middle, so that way we can cut it in half. And then we are going to look at the first half and the second half. And it's going to keep doing that until it gets down to the two elements. Okay, so this while loop allows us to implement the division of the array into the halves, so that way we can fulfill the requirement for the binary search. So here in the while loop, you would have the M represent the middle, and you are going to do the left plus the right minus 1 divided by 2, because that will represent the middle mark of our array. And then we are going to check it against, so if you have an X, X going to represent the mid, and we are going to check if array of M is going to be X, then it's going to return M. Okay, so here what we accomplish here is we are going to find the middle point. Now, then you are going to compare the upper half with the lower half, the left and the right. So if the middle is going to be less than X, it's going to take that middle, it's going to go to the next one. So it's going to do an M plus 1 to the right of that. Then else, we are going to have the right where we're going to seek M minus 1. So this is how we can zone in on the left and the right side of the array, so that way we can actually identify our key. So here, after you define your function, which is binary search, you would then implement the main function. So in the main, of course, we have to declare our array, and we would initialize it with the value that we want to use. And keep in mind that with binary search, we want to come in pre-sorted. So either you manually put it pre-sorted, or you would have to implement the sort function. So otherwise, it would not work in the case when we have it. So they're here, then we would have 2, 3, 4, 10, and 40 going from low to high. Then our X is going to be 10. And so what we're going to do is we're going to look for the 10 in that array. That's the key, is going to be X. Okay. And so if you look back from our function, you would see that we want to look at X. We want to compare X to what is the middle point of the array. If it's greater, it's going to seek it on the right side and ignore the left. And then if it's smaller, it's going to seek it on the left and ignore the right. Okay. So our key is going to be 10. That's the value that we're going to look for. Now the N here represent size of is going to be the number of the array, and it's going to be divided by the size of the first element. So that's going to give you the number of elements in your array, which is N. Then we are going to be able to have the result variable, and then we simply will call the binary search function, which we previously defined, and then we would have its argument. So we would have the array, right, 0, N minus 1, and X. So then after that, we would then be able to display some string and plug in the result. Okay, so we want to be able to identify which index is that value, so it can go and find it for you real quick and give you the index, which is the location. Okay, any question? Okay, so here it gives you the explanation just like what I've gone through. We would compare X to the middle element. If X matches the middle element, it's going to return the mid index. Okay, that's in our function. Else, it's going to look at the greater than the mid element, then it's going to go to the right side. If it's less than, it's going to go to the left side to find the X. And so now when you determine the number for the elements, we would look at the comparison. So when you write this program in, first you would write the program and run the program. Then you have to determine the number of the comparison in the elements in that array. So how many comparison would you need in order to be able to achieve that that search? Okay. So while you're working on that, give me a second. Let me get to REPL here. I normally have everything on my laptop, so sorry for the log in real quick. REPL's a little slow today, right? Or I'm just on a slower network. Okay, so as you run the program, take a screen capture. That's what we need. And what the objective of this is to show you how you can approach binary search using different techniques. So the first technique is that we are going to loop through it. We're going to narrow down on the middle, and we're going to keep using the while loop to cut it down on the middle and compare the value, okay, to the middle point. Then we're going to look at other techniques on how we would be able to implement binary search. Yeah, I'm unable to get on REPL on my side here at MVC. It's a Murphy day today. Everything is just like, takes a little longer than usual. To REPL real quick. I will have sorry, multi-factor authentication. So it wants to validate 3 times. So second, let me get my verification code for my REPL. Go back to screen share. Okay, so here's the program. This is what we have in the assignment. When you run this, it should tell you that this is going to be at index 3. So 0, 1, 2, 3. So that's correct. We should have it at index 3. So after you run the program, what you would need is you would need to determine the number of comparison for your 5 element. Now, if you go back and take a look at our assignments that we did, right, and it also gave you the equation. So in the, you would have log 2 of n, or you can take natural log of n divided by, so ln of n divided by ln of 2. So that will be your t of n. So when we call on the calculator, put it into scientific mode. And we know that n is 5, so sorry, I'm frozen at the moment. Oh no. There we go. All kinds of issues with technical issues today. So L of n, natural log of n, so we would have ln, and how many elements do we have? 1, 2, 3, 4, 5. So you would take 5, and then you divide it by natural log of 2. Okay. So if we put in 5 and we take natural log of that, and then we divide it by 2 and natural log of 2, that's going to give you 2.3. So we can round that down, or if you want, well, I guess worst case scenario, we could probably round it up, but let's say that we just do 2. So that will be 2 comparison. Any question? So when we have 5 element, we simply plug that into our equation, and you can do log 2 of n, which should give you the same thing. Any question?
Professor, what does the return of -1 represent?
Yeah, so if it's not there, because what we do is we have to check, right? When you have, if it's not there, then you want it to have the return -1. And we don't do return 0 here, because the whole point in having a function is to return something, okay? And so when we just do the -1, that's just to, if in the condition that if when it exit, it would then return -1. So that means what? If my x is at my m, it's going to return -1, that it's going to say that that is the value for x. But if you don't do a return here, what will happen is that's no point in for us to write the function, because we can simply implement the while loop inside the main. So that would just, when you return here, you would give the resources back to the system. So if when we reach the element and if it's not present, so let's say that if I'm looking for number 50. And in my values, I have 2, 3, 4, 10, and 40. If x is going to be equal to 50, it's going to return -1. Okay, just showing that it's not able to seek the value based on what is initialized. Okay, so that just allows us to not enter the loop and be able to implement the algorithm for the binary. If the element is not in the array, we won't have to enter this.
Thank you.
Yeah. Other questions? So the thing that's probably new to some of you that haven't done the array this way, right? Because traditionally you're taught to do the array and you have to put the constant size of the array. But when you initialize your array, it automatically know how many index it is. And instead of using 5 as the number of elements for that array, what we can do is we can represent it with a variable, and we can use the keyword size of from the array library to be able to tell it that my array size is n, which is the number of elements in the array. And this is how you write it. Okay. So I know in the last few weeks, some of you had issues with Visual Studio not seeing your array, or not building or not compiling the program, because if you didn't put in, the array size, it did not allow you to do that. So there are several ways that you can approach that. You can approach that with the constructor, where you use new and then you build out, you would construct an array as a dynamic array. But another way that you can do this is you can implement something like this, where you would take the n, and the n would represent the number of elements in your array, and you simply bring in the array library and then use the size of. Okay, you're going to see this more often from here on out. So this is another way that we would be able to, right, represent the size of our array. So once you run this, you get an index. We see that it does do about 2 comparison. And if you're looking at the time itself, so let's say that if your processor takes, right, like 1 second to do 1 comparison, then it should be able to complete the program and find the value at 2 comparison at 2 seconds. Okay. And, in that sense, we can also measure it using the time library, but in this case, we manually calculate it out, and we would see that it is 2 comparison, that's what it does. Because why is it doing 2 comparison? Let's take a look at the algorithm, right? So if you have an array, you're going to break it into half, the first half, okay, and then the second half. So it's going to then find the middle point. Now, the middle point is going to be 4 in this case, because you have an odd number of array, and you would see that that's 4. So it's going to then first compare it to 4, and it's going to say that it is higher than 4. So that's 1 comparison. Then it's going to zone in on the right side. Then it's going to be able to find the 10. So that makes it 2 comparison. Okay. So when you calculate your T of n, that's going to give you the comparison. Now that is going to be able to tell you how the computer is going to be able to seek that value based on the program, the algorithm that you implement there. So in this case, it's true to what we calculate, right? Unlike last week. So what you see is you see about 2 comparison. That's how it's going to be able to find that. Now for B, I just need you to explain, right, the processes in finding 10 in that array. Just look at the functionality in the algorithm, and I mentioned it a few times already, of your program, right? What is the while loop saying? Okay, and how is it used to be able to divide and compare the middle value? And then when the function is called, what is it doing there? So the whole point in this is to make sure you understand how to implement an algorithm like binary search. Any question with one? So give me a few sentences for 1B, okay? So as you look at some of these programs, you're gonna say, well, that can't be just one way, right? We would look at another way that we can implement this algorithm. And I think we talked about possibly we can implement recursion in the lecture for this week. So let me get my program open up. Okay, any question on one? All right, so in number 2, you're gonna look at the program, you say, well, it looks kind of like the other one, but let's take a look at it closer. So here it tells you the procedure for the program. And this is really important to point out for those of you who are thinking about, how am I going to be able to approach something like this? Well, you have to really have some kind of procedure, and that's how you're going to be able to use your procedure as algorithm that you want to implement in your program. So just like the other one, we are going to compare x to the middle element. And if it matches, it's going to return the mid index. Else, we are going to look at to see if x is greater than the mid element, right? If it is, then it's going to go to the right. If it's less, it's going to go to the left. Okay, that's what these for. Okay, and then so when we look at the program, instead of having the while loop in that we would divide up our array into halves and halves, we simply implement conditions. So again, you are going to have array as a library, as STL. You're going to bring that in, and you're going to bring in algorithm. You have a binary search function, and you are for your parameter, you're going to use the array, the variable L, the variable R, and the variable X. L for left, R for right, and X is your key to search. And so when you use recursion, you have to think about how it's going to build on the prior index or value. So here we simply check if R is going to be greater and equal to 1, then the mid is going to be left plus right minus left divided by 2. So L plus R minus 1, okay, divided by 2. So that's going to be the one to the right of it. I mean, the one to the left. Yeah, the one to the right of it. So minus 1. So you have to visualize that. If the element is in the middle, it's going to return mid. If the mid is greater than X, we are going to return the binary search. So recursion is about a function calling itself. Okay? So here we have the binary search function, but we would check if it's greater than X, it's going to return, and here it's going to call. Okay. And in the parameter, we would have the array, the left, the mid minus 1 plus, and then the X. So here, if you read the comment, it says that if the element is smaller than the mid, then it can only be present in the left subarray. So why am I doing a -1 here? This represents the left side, right? The middle to the left is going to be subtract 1. The middle to the right is going to be +1. And for the if condition up here, yeah, so if this is true, then it's going to turn again. It's going to return, and it's going to call the binary search function, and it's going to go to the right, and it's going to look for X. Okay. So logically, you have to think about how you would divide up your array into half, and you would design a function that's calling itself. Okay. Now for the return 1, it's going to be an element that's not there. So like what we talked about before. So just like the other program, it's very close to it, except that we got rid of the while loop and we implemented the nested ifs. And we also use the call, we call the function within function. And then in the main, it's pretty much the same. You would have the decoration of your array, and you initialize the value there. We would also define what our key value is, which is X. And then we would specify what size of the array is. And then we want to store the result. So in the result, we're just going to call the binary search. Okay. Very similar to the last one. The main difference is this area right here. Okay, so now if we run this, it's still going to give us the same output as we are using the same value in our array, the same size of array, and the same key. Now, if you want to test how recursion works in the search for binary, right, we can test it with a larger array, something that would go above 100, 200 elements, even 1,000, and see how that will be. Because when it starts calling on itself, right, it's going to build on the immediate return from its own function. So is it going to be effective? So here, after you run the example 2, take a screen capture. I just want to know that you know how you put that in, you run the program. And you are going to give me the functionality of the program implemented. Okay, describe the functionality. So you can go to the function itself and explain how these if statements are used. Questions? Okay, after you had stated, right, the functionality of the program, you can compare the example 2 with example 1. Which program is more efficient? You can explain your answer. And in the past lab, we talked about whether recursive function is effective or not, right? The benefits of it. So when you read the code for recursion, it's clear. It's very clear on how we implement the algorithm. right? Go to the middle, check the middle. If it's not, move one to the left or move one to the right. It's very clear. And then we simply just return and we call a function call itself. That's one of the benefits. Okay. But if you compare this to the other program, how is the other program differ? Which one do you think is better? Now, the only way that we can test, right, with these two programs is to be able to measure the time that it uses to be able to output that. So when you implement if conditions like this with the recursive function, right, you are going to have a certain O of n compared to when we implement a loop, which is iteration in the other one. And when we test this type of program to be more consistent, we would run it many, many times to have an idea of our performance time, right? Your time. So here with recursion, we also give up space. Now, on the larger array, we can consider using pointers or use data structure. Okay, instead of a simple array, if you have like a very large set of data, you want to consider using data structure, such as, you know, a linked list, a doubly linked list, and so on. Any question with number 2? So also this week we talked about jump search or jump search, right? You will find jump search information more readily available compared to if you're looking for chunk search. So the common name for it is jump. And keep in mind that all of these searches works best with a sorted container. So instead of linear looking at every single element, we can group them up and compare less. Okay, so we would check fewer elements. So it is a way to do linear search backwards, but we would do less of a comparison in our container. So your optimal size for the chunk is going to be square root of n. N is going to be the number of elements you have in your array. So in this example, we have 0, 1, 1, 2, 3, 5, and so on. So what we can do is we can chunk it up, and it's going to be able to seek by jumping from one chunk to another. So if we have an array of 16 elements, right, and we need to find the number 55, what it's going to do is it's going to jump from the first chunk to, and then look for the highest value, then go to the next chunk, compare that to the highest value, and so on. So as it gets to the element at the index 12, that's going to be greater than 55. It knows that it has to be inside here. Okay. So that gives you a little bit more understanding on the jump search. All right, so now let's take a look at the program. I tested many different programs. These are the ones that made it to your assignments, to your lab. Some of the other ones are great. It just, might be very complex too. We will take, eventually you're gonna see more stuff on vector and class and structure, struct and stuff like that. It just, I want to build you up to it. Okay. So we are gonna look at the simplified version. Okay. So here is the program for number 3. And in this one, we are going to implement CMath because we are using square root. We're also going to use array STL and algorithm STL. So we start with defining a function called jump search. And it's going to take array, variable X, and variable N. Then we want to implement the procedure for chunking our array. So we would have a variable called step, and that is equivalent to our chunk. Then we would take the number of elements and we would take a square root of that. So that way the system would know how many elements is going to be in step or in a chunk. Okay. So just like how you do calculation, you would start with finding the chunk size. And then we are going to narrow down on which chunk, okay, which chunk is going to have our value X. So here is where we would check to see if the value exists in certain chunk. So we would implement a while loop. Okay. And in that, we also use the array, but this time what we're going to do is we are going to let it look at the chunk or the step. And as it goes through, it's going to keep taking square root of n and examine each of the chunk. So if the previous is greater than or equal to n, it's going to then return -1. We're still going to have to implement linear search inside each of the chunk or the block. So we have another while loop, and we're going to let it examine. Okay, so here we are going to set up a minimum. If it gets to the next block, that means that it's not there, so it needs to return -1. -1 is when it's not found. Then if, right, it finds the X, then it's going to narrow in on that. So as you can see, you can simply use while loops and nested if statements to be able to implement jump search. Now, can this be tighter and neater? Sure. Right? So here is our main. We have an array. We initialize our array. We're going to look for number 55. I just want to double check and make sure. Now these values, you see they're not sorted. Okay. So if you want to have a pre-sort, you can, but we're going to test it that it's not sorted. And then our end-to-end is the same, the size of the array over the size of the first index, which is 1. Now we're going to have index, and here is what we're going to call the function. And we are going to use array x and n as arguments. And we're going to see out the index. We want to see the location of 55, which is right here. Okay. So when we run this, it tells us that it is at index 10. So simply reviewing the comments is going to give you the general idea of how the program is working. Okay, so then we wanted to use this program, run it. Okay. Then we are going to determine the chunk size for the 16 element array. And that's really easy. We did that in the program itself. So, you know, you can do insert. I have a square root that's already here. Instead of looking for it. All right, so my chunk size is going to be square root of n, which is square root of 16. Equal to 4. So that means that it's going to be 4 each, right? Like this. And so on. And for jump or chunk search, we know that the comparison would be 2 times square root of n to find the number 55. So if we calculate that, we already have the square root of n is 4. So if we do 2 times square root of n is going to be 2 times 4. That's going to give us 8 comparison. So why am I saying 8? Because if you look, right, if we manually evaluate this, okay, so we have first it's going to do 1, 2, so it's going to have to compare to the first chunk, right? It's larger than 2, so that's 1. It's going to be larger than 13, that's 2. Then it's going to go in and it's going to evaluate. It has to do this, this, and then it's going to find. So it has to evaluate each of the chunk first, and then it's going to come and it's going to look at how it's going to zone in on the actual chunk, and it's going to be able to find the 55 in the third chunk. So that's going to give us a comparison. Now this is way better than doing 16 comparison, right? Like going through, because this is not ordered, so it would be doing an unordered linear search where it has to go all the way to the end because I don't have them sorted. Okay, even if I have them sorted, it's still going to seek. So for the ordered one, it's going to stop here. So 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be about three comparison higher if I have it sorted. Okay, then for part C, we're just going to explain how the program function using the algorithm. So we can focus on the function definition, how it's using for, so first you can talk about how it divide up your chunk or your block. Then it's going to be able to determine, right? And if you want to be technical and specific, you can. Or you simply, I want you to understand how that works as the function. Any question? I didn't focus on the linear search because linear search, you simply implement a for loop or a while loop. It's really simple. So to really look at each of the index, right, and then do a comparison. Is it equal to that? Is it equal to that? And it's not worth the time to just really look, because we should look at a little bit more advanced type of algorithm so we know how to use it. And again, like I said, this is only one way to approach jump search. You will find other ways, okay, by using the while and so we can implement the condition there. So for C, please explain the functionality of the program, how it's using the algorithm. Any question with 3? Okay, no question. The next one is very easy. It's very short. The reason why I added this was I want to show you that the quick sort is implemented in C++ sort function. Okay. And so internally, it uses an algorithm called intro sort. Now, there are sort algorithm that is mixed. That means that it takes different sort algorithm and then implement it. Okay, like the intro sort implements quick sort, heap sort, and insertion sort. We talked about insertion sort in class, right? And then when you take 17C, hopefully your instructor will talk about heap sort. But quick sort was covered in 17A, supposedly. So when you use the sort function in C++, it is mostly quick sort, but it has some mix with the insertion and the heap. So by default, it tells you here that it uses quick sort, but if quick sort is doing unfair partitioning for the n log n time, then it's going to switch to heap sort. So it can go both ways. And then if the array size is too small, then it's going to go into insertion sort. So when you use this, keep in mind that it is a hybrid and it can go either quick, heap, or insertion. Now on example 4, we would see that we would use the sort method or function. Sorry, I'm so used to Python, call it method. Then we would have a start and an end. That's going to be your parameter. And the start address is going to be the first element of your array, of course. Index 0. And then the end address is going to be the next contiguous location of the last element in the array. And it's going to rearrange your element based on, and notice that it puts address because the values that you put in there, you initialize, it stores it at a memory location. So that's what it uses, is an address. Okay. All right. So the program is very simple. We have a main function. We include array and algorithm STL. In the main, we initialize our array as ARR. And then we specify the size of our array. And then we would use the sort. So in it, we would use, right, the starting address and the ending address for the argument, the parameter. Then we would print, and in order to access the array, of course, you have to loop through each of the index in order to print out all the values, because we wanted to see if it's sorted or not, right? So we just access the index of the array and print that out. So is it really storing things in contiguous manner? No. When you issue the sort mechanism for it here, when you tell it to sort as a function here, what it does when it gives you in the array container is it associates different addresses in order, so that way it becomes sorted. Or So when we run this, right, you should have a sorted array. One, 5, 8, 9. Let me see if it matches mine. Yep. So what I wanted to show you here is that we already have things that we can use, but we have to understand what they are in order to use it. Yes, you can write your own sort algorithm, but if you want to use sort, this is what sort would be. Okay. So explain the sort functionality of the program, how the values are compared in order to be rearranged. So quick sort is very close to selection sort, which is the last item that we covered in the lecture the other day, right? It does have a binary approach in that it's gonna take, right? It's gonna take and it's gonna be able to section it, and it's gonna compare and swap. Now, if you wanted to read more about what quicksort does, if you don't recall that from 17A, you can also find this right on C++ or other area you will find it. So keep in mind that this sort mechanism, this sort function is a mix of those three. Okay. So in selection sort, we talked about selection sort in the first round. What it does is going to look for the smallest value, right? And then it's going to take that and it's going to bring that value, it's going to swap its place with the first value, the first element. So the 0 and the 1 is swapped. Then it's going to go again and it's going to take the next value, next smallest, I'm sorry, which is 1. Now 1 is moved back here. Then it's going to swap it. So we're going to do selection sort next so you can see. Now, quick sort is not quite exactly like selection sort, but it's very close to it. Okay. As far as T of n, it's very close. Okay, any question with this one? It's not even, what, 15 lines, so it's not even that long. Okay. So run the program, explain the short functionality of the program, how the values compare in order to rearrange. Then we are going to do selection sort. I know this one's a little longer than usual, right? But not too long. So for selection sort, it's going to focus on the minimum value. And what it's going to do is it's going to divide the array into 2 subarray. One section is going to be non-sorted, while the other, as it arranged, is going to be sorted. So every iteration you would see that from the unsorted subarray is going to be moved to the sorted side. So if we look at this array, 64, 25, 12, 22, and 11, we want to make sure that it's going to go from low to high. So it's going to look at the minimum value, which is 11, and it's going to move it to the front, and the front of the array is going to be the sorted side. Okay, so 11. Then the next minimum is going to be 12. So 12, right? The last half of the array, as you can see, remain unsorted. The front is going to be sorted. And then it's going to go to the next value, which is 22, and then 25, and then 64, and it will be done. So if you have a procedure like this, you have to think about how you would be able to swap the value, right? Because we have to be able to move 11 to the front and then 12 to the front and so on. So the lower index would be the ones that are sorted. And in this one, we are going to use pointers. I know some of you don't like using pointers, right? But you have to practice using pointers so you can get better at it. Okay, so let's talk about the program itself. We include array and algorithm STL. We have a function called swap. Remember, we're gonna move these numbers. So, and the best way to do it is to use pointer. Okay. Now, for the swap, we don't need to, it's not returning, so we don't need to, we can use the void instead of other data type. Okay. And we are going to use XP and YP. Those are integers. So your temp is going to be pointed to XP. XP is going to be the same as YP, and YP is going to be temp. And that's how we are triangularly moving it. Okay, so first we point to XP, then XP point to YP, and YP point back to temp. Is going to be temp. We reassign temp to YP. And all the swap functionality is just like that. A temp location point to a variable, another that variable pointed to another variable, and so on. Then we have selection sort function. It's going to use array and int n. It's going to be the number of input or elements in that array. We are going to loop through it. So we are going to implement the for loop, which has 3 parts: minimum, maximum, and update. We have to find the minimum element because that's going to be in the front of our array. So we would say that the minimum index is going to be I. And for the nested for loop, the second for loop on the inner for loop, we would have J is going to be I plus 1. J is going to go up to the end of our array, which is n, and it's going to update, increment. If this is going to be less than the minimum index, that's going to be, J is going to be the minimum. Now, we're not done. That is just for us to look at the minimum element value. Then we have to do the swap. So here is where we call the swap. And remember, if you point to something, you have to dereference it. So here is where you would dereference. Okay. So we will do the swap when the minimum element is found. We're going to put that into the first and then the subsequent. Then we simply just have a function that print. So we just loop through it and then we would print out the value. So your main is your driver. We initialize our array, right? Its size, we call selection sort. That's the main function of our program. Okay, and then we call on print array. So we can see the sorted value. So there we have it. So in this program, you can see that it implements, we use function for swapping, function for sorting, and function for printing. And that's a better way to do that, okay? To be able to use tasks separately. And then you have one function calling another. So you have the selection sort calling swap. Okay, and then in your main, you call the selection sort and the print. And we can troubleshoot it better if you have it in separate functions. So you can go through and fix the problem if it's not working like how it should, compared to if you put everything in main in one huge program. Then you have to comb through and fix the problem, and then so it's cleaner if you have it separate functions. Okay, so run the program, provide the screen capture, tell me how selection sort is implemented, how it's able to rearrange the values from the lowest to the highest. This program uses nested for loop, which gives us O of n, or T of n is n squared. Okay. And so we simply plug in n. It's really easy. You have 1, 2, 3, 4, 5 element. So T of n, right, is n squared. So that will be 5 to the second. Which is 25. So as we see, that's implemented here. So in the iterative approach, that's your T of n. As you loop on the outside, that's the number of elements. And then you loop on the inside, that's also the number of elements. So you take that, you multiply. So we would have 25. And so that means that it has to go through those elements, right, to be able to rearrange it and give you the sorted container. Sorry, I'm in the classroom and the lights keep turning off. All right, any question?
Professor, I know we're dereferencing the swap function, but is that also counted as a recursion as well?
No, because it's not building on, it's not calling itself in any way, right? Like swap doesn't call itself. All that is we call swap and then we have to dereference what we pointed, right? Because if you don't, you won't be able to get value from because when you point, you just point, you're gonna go, you point to the location, the address, right? So when you dereference it, it's actually gonna tie that value to what you pointed to. Okay, so now if it's not a recursion, because if it's for a recursion, then it, you know, here, then it's gonna have to call itself. Okay. But what you're doing here is you simply reassigning the pointed value. That's what you're doing in the swap function. Because if you look at it, it's a 3-step, right? I have a temp variable, I point to XP. Then I go to XP and then I point to YP. So it's like I'm the temp variable, I point to you, and then at where you are, you're gonna point to another person. And when I get to that person, it's gonna point back to me. Okay, so it's a 3-step. So when you dereference that, it's gonna be able to go back from temp, I'm sorry, from YP to XP to temp.
I see the triangle that you mentioned. I see.
Okay.
Thank you.
I always think about triangular move
Yeah.
when I look at swap. So, and the important takeaway in this is that you can't, so when you look at something linear like this, a lot of people say, oh, we'll just swap it, right? Like take 11 and put it there. It doesn't work like that in the computer. You have to take it and put it in a location and then take that 64 and then put it into another location. But the computer doesn't move things around. All it is associated value at a memory address and be able to retrieve those values so and present it to humans. So you have to think of it that way. And it's perfect using pointer because, you know, we don't need to move things around. We just need to point to the appropriate things that makes it look like it's sorted or in order. And that's all we need to do. All right. Other questions on this before we get to merge sort? So here's the merge. It's divide and conquer. It's going to take things and break it into halves, like what you've seen in binary search, but we sort it. Okay. So we take this, we break it into 2 subarrays and then 2 subarrays again. And when it gets to the single element, then it's going to merge back. But as it merges back, it's going to compare. If the lower one is going to go into the left, the higher one's going to go to the right, and then so on. Then it's going to merge from 2 elements to 4 elements, and the lower one's going to go to the left, the higher one's going to go to the right, and then lastly, it's going to merge back to its original container size. Okay. And yes, I stole this from a website because I didn't want to sit there and draw it. So it gives you a little bit of visual there. Okay, so now let's take a look at the program. We still have a lot of time, so. And I want to show you this. So in the case where you have to write, search or sort, the common ones that we talk about today, at least you know how to approach it. Okay, we have a function called merge. Okay, and we're going to use left, middle, and right like what we've seen before in our array. inside this function, we declare variable I, j, and k. And we also have variable n1 and n2. So the middle is going to be the middle subtract left plus 1 is going to be your n1. Okay. Because remember that we have two subarray from our original array. So we want to represent a certain number from left or right, like in order. Okay. And your n2 is going to be the right subtract the middle. Then we are going to make our array. Okay, so we would represent, remember the picture, the left and the right array. Should be indented. C++ didn't care too much there, so, but Python would have complained. All right, so now what we're gonna do is we are gonna loop using an outer loop. And we are going to create the temp array for the left and the right. Actually, I was right the first time. Okay, so the left is gonna be your first loop, and the right is gonna be the second loop. So what it's gonna do is gonna place the value into two separate arrays. Like we would move them into two separate arrays. Then we would initialize the first and the second array, okay, as 0. And then we would have the index for the merge array when we put them back into 1. So first we have to separate them into left and right, two subarray, right? And then sort them and then put them back into one array. Merge, that's what it's called, right? So then we have a while loop. And here it tells you that while your index is less than n1 and, right, your index on the right is less than n2, and then you nest an if left is less than right as an index value, then we merge it into one array, starting with the left, because the left is lower. Else, we're gonna merge it. We're gonna merge the right array. Okay. And then we have to go through and recopy all the elements again because we separate them into subarrays. So we've got to put them back into the original ARR as 1. So we would copy everything back using 2 additional while loop. Now, is this the best, neatest? No, right? You would see that, you know, as you separate them across, you have to put them back and you have to implement the loop for that. Okay, so we would then copy everything back into ARR. Okay, so remember that this is the merge. This is only to combine the two subarray back to the original array. The sort mechanism is when we need to compare. Okay, so if left is less than right, then we would implement the equation. So the middle is going to be left plus right minus 1 divided by 2. You saw this earlier. So that allows us to control also overflow. Then we would call merge sort, and here you have a function that call itself, right? We saw this earlier. And so we would do to sort the first half on the left and the second half on the right. Because you have to sort them before you merge them. So after you sort them, you call the merge. Okay, so we have a sort function, sort the left, sort the right, and then merge. And then we have another function to print. So we would be able to access each of the element in the final array and print them out. So in the main, we initialize the values for our array, for the elements in our array, the size of our array. We declare that. Then we call on the print function because we wanted to see out. And then we call on the merge sort, which calls the merge. Okay. So we started with the given array, which is this. And then when we sort it, it's going to go ascending. So as you can see in this program, we broke the procedure down, right? Like technically we divide everything into half, right? We divide and then we need to conquer. So we need to sort and merge. So with that, we just write the functions and have a function call another function. And there you go. So last one. Okay, here I also explain it. Write the program, run the program. Okay. And then you are going to calculate T of n. So your T of n is going to be n log of n. So how many elements did you have? You have 2, 4, 6. So that will be 6 times log of 6. And then you can use your calculator, right? Put that in there and be able to calculate. Then for B, we're just going to explain how merge sort algorithm is implemented in the program. So we want to focus on two functions. We want to focus on the merge sort and the sort. Okay. And you can talk, or I'm sorry, the merge and the merge sort. So the merge, you talk about how it's able to look at the left and the right as it combines it into the array. And then for the merge sort, you can talk about how it's able to compare, right? And here it implements recursion. So okay, any question? So today we did more than usual because this chapter has quite a few concepts on search and sort. But like I said, we haven't hit all of the major ones even, right? But at least you know how to do binary search, you know how to do merge sort, selection sort, jump search. And when you use your sort algorithm or sort method functions in from the library, you would know what that's capable of. Question. This I used to use in the past, but I kind of want to show you since we have a little bit of time. This uses vector. So as you can see, vector does a little different in that we have it is able to grow with the actual size of the container, right? And then we would do a beginning to end. So it's slightly different on how it's evaluating the index there. So you can definitely use a binary search. It's already built in. If you include algorithm, you can use binary search and sort. It's already there. You don't have to write it. Okay. So you just need to include the library and then you just use the function and the argument and its parameter. So you can do it that way. Now, if you use sort, we talked about sort, we didn't talk about binary search. So there is a function that's already pre-built for algorithm library. Any question? All right, so if you're finished with today's lab, you can go ahead and submit it on Canvas and then not worry about it, but you do have until Sunday. Okay. And you can type your name into the chat for attendance record. Have a good night. I'll stick around for questions and I'll stop recording.